Well, first off, thanks very much for having me in this morning. I appreciate it, and especially in the quick turnaround. I think we just talked last week about setting this up, so very impressive. My name is Sean. I'm from Faro. I'm actually from the Toronto area. I'm in North York, so I think it's 23 minutes away according to Google Earth today. But I work directly for Faro, so you're dealing with Faro itself. So Faro itself is an entity from McGill University. The original founders were grad students there, and we're working on creating a articulating arm to do measurements for the human body to see how much your leg can bend and check the angles there, which I find interesting because I actually had my ACL replaced this summer, and watching them see how much actual flex I have in my leg throughout the 6-month ordeal since then has been kind of interesting. But they decided to move more to the industrial side of things and created the FaroEdgeArm that you see here with the probe tip. We've been in business ever since. They moved to Florida about 9 years later, so about 20 years ago they moved to Florida in Lake Mary, Orlando, or just outside of Orlando and Lake Mary, and have been there ever since manufacturing the arms. We do have offices around the world. So first off, our mission is to enable mankind to easily, accurately connect the physical world to the virtual world. So not only are we able to scan and measure with the probe tip, we have multiple equipment that will do various types of measurements. So we actually can scan this classroom, this entire campus, this building, things like that. And I'll go through that quickly in the slides. So yeah, so founded in Montreal in '81, and since then we relocated to Lake Mary, Florida, traded on the NASDAQ, and we've been acquiring some companies in the past few years, including a Canadian company out in Vancouver that creates software for our 3D Faro Focus scanner. We're doing, they use it for crime analysis, for police forensics. They use it for architectural designing. It's called BIM. So worldwide network, as I shot ahead in my previous discussion, but world network. So we have offices in Germany, Singapore, but we are headquartered. I will silence this so it doesn't happen again. Based out of Lake Mary, Florida, here in Orlando, just north of Orlando, but with offices. We also have an office in Germany, Stuttgart. We have a training facility here in Mississauga. We just acquired another company in Vancouver, so we have multiple offices, including one in Michigan as well would be, I guess, another one. So the family of products we have, and I actually have to update this slide, because 2 weeks ago we replaced the 3D imager called the AMP here with a system called the Cobalt, which, same idea, it's structured light, so it creates a point cloud for you to be able to process and do your analysis on the parts that you're scanning. Or in your case, I think you're looking at doing reverse engineering, it creates that point cloud. But the new Cobalt is a much more powerful system. It's a dual camera system, so it's got the one projector, but it's able to take 2 shots at the same time and combine that data set into one data set. Remarkably fast. I got trained on it yesterday and was blown away by its speed. Accuracy, depending on which lens, you can also change the lenses on the new system to a 250 millimeter or a 500 millimeter lens to allow for greater accuracy or greater field of view.
Question, the 3D imaginary. How it moves the user move the ones?
The imager, it sits on a tripod, and you can have it move around the part. Like if I was to do this table, for example, I would rotate around it. Or it can go on a robotic head. It can also go on, you can use a rotary-based platform, so you can put the part on a rotary system, and it rotates as it's scanning. So it would take an image, rotate 20 degrees, 90 degrees, take another shot, and then take a third, fourth, fifth, as many as you need to create the entire the data set for that part. So I'm here today with the first one here is the gauge and the edge arm. We have actually another one called our Prime that we still sell. Those are arm-based products. The gauge is a 6-axis arm as well as our Prime, whereas the edge that we have here is a 7-axis arm. And with that 7th axis, it allows us to attach, I don't know if anybody saw when I first came in, but there's a not only does it work as just for probing with the probe tip, and I can move it around and do my measurements, I can attach a 3D laser scanner at times if I need to have actual scan data or your point cloud data set. And then we also have the Faro Focus. So this is for the BIM projects, the architectural projects, or your a lot of forensics, police investigations will do this. So it's a 3D scanner, but for long range. So you're not getting the accuracy that you're getting from the ARM or from our 3D imagers, such as the Cobalt or the AMP or our laser line tracker. We're actually at that point collecting this entire room. We're collecting the entire campus. If you've driven under the Pickering Bridge, the new GO Bridge under there, I used a 3D scanner to collect all the data on there for doing measurements for the zip skin they're putting around it with all the lights. So that's how they collected all that data, was with the 3D scanner from long range across the highway to be able to do the measurements. But you're only looking at, say, 1 millimeter accuracy versus, down to a thou accuracy with an ARM. So that's where the differences are. We also have the Freestyle, which is a handheld laser scanner to do, maybe this room is a bit too big for it, but for doing large objects as well. And again, we're at about 1 millimeter accuracy for that as well. So you're not as tight as our high-end metrology, high accurate models that we also sell, like the ARM. So we're in various areas, aerospace, kind of comes into Eric's world. Here you have aerospace again, you have two trackers. So a tracker is a single laser shot coming out, and it's high accuracy up to a very large range. So you can measure up, say, 80 meters from the one tracker and be able to measure whether it's the circumference of this rocket here, or if you're doing this room, you can measure all the corners. A lot of places will use it to fit glass to make sure that their glass drawings are done properly. They go out and measure, such as the Pickering Bridge, to do all your measurements at a long range, but high accurate capabilities. And then we have also automotive area. So we're looking here at doing, the gentleman you can see on the screen, it's hard to see, but he's actually laser scanning this chair. And so a lot of the work going into your car when you buy it, it's not just, putting it all together, putting the engine in and driving it away. There's a lot of inspection going on. And a lot of that's done with the FaroEdgeArm and Faro scanner. And for an example, this is a chair here. They actually, what they also do, some of the companies will put I'm going to call it a dummy for lack of a better word, but a mannequin into the seat and weigh it properly to represent, say, my weight. And what they do is they actually check the hip placement on that dummy to make sure that the foam is actually sitting properly. And if it does, great, it passes. And if it's not, it's rejected, and that line's, they have to redo the foam for that line, and they go back to the manufacturer of the foam to make sure that the foam's to the proper quality. So everywhere inspections needed, they typically will use a device such as the ARM to check that. And this gentleman's using it as a scanning probe, so he's not just probing, he's actually scanning. And the nice part of that is you're not actually touching it. So obviously, if this is a leather chair and I put any pressure onto that leather, it's going to distort or change the shape of that chair. I mean, even just sitting it, you sit down and it compresses a bit. Whereas laser scanning, it's not obtrusive, so you're able to collect that data and get it as is. So basically, exactly how it's in its state when you're looking at it. Another area you could do if you're doing welding. I had a gentleman call yesterday for doing welding, and he wanted to check before and after he did the welding to that part to see if there's any deflection or change, spring back, things like that. So by scanning it in its natural state, welding it on, scanning it again, you can see if there's any deflection in the actual steel. Just another example of automotive. Here they have the ARM doing inside. I'll just fire through these, doing some more long-range scanning with the tracker. So the ARM itself is a portable CMM machine. So typically a CMM, you see there's an image here on the right. That's your CMM machine. It's a large granite table. It's computer controlled. It's able to do very precise measurements over and over again of the same part. Now, that's a fixed CMM. With the ARM, we have the ability, it's lightweight and portable. I brought this in the back of my car today and wheeled it up here, no problem. But it's also very, very highly accurate. And I have the ability now to not just only measure on this table, I can now take it to an actual machine in the factory and do my measurements while it's still in, say, a CMC machine, or do the actual measurements live, not having to take the part out and then if it's a good piece, put it back in the machine and get in the exact same spot to continue milling or machining. So I have the ability to have a lot more versatility with the actual arm itself, and typically much more affordable than a fixed CMM. With a fixed CMM, I'm also having to program it to do all the commands and do all your measurements. With the arm, I'm literally just bringing it out and moving it around, and wherever I touch with the probe, I can take a measurement. And then also the ability to laser scan at the same time. So these are just 12 reasons why to get a FaroEdgeArm. I'll just skim through them, but it's designed to be in a clean room, but also on a shop floor. So it doesn't have to be in that, a clean precision, dust-free room. It's designed to be in the industrial world. There's no need to sticker up the part. I don't have an example here, but some machines you need to actually put stickers or targets on that device to be able to align it together. With the arm, you're actually getting its coordinates based off of where the arm is. So right now it would be off of the base here. I could change its coordinates to a CAD coordinate system or to any reference system I want to. But when I do my laser scanning, it's getting all that information from wherever I move the arm. So there's encoders and every single movement up here. And this one I mentioned earlier had 7 access arms, so it's got 7 areas it moves. So no programming, but I have the ability to then do the same job. If I have 100 of the same parts I want to do, I can actually write a macro so it walks me through. So I am able to still do duplicate jobs very easily by programming a macro to tell me which to measure and where to measure, but I'm not having to program a computer-controlled robot or anything like that. So you mentioned the no prep work or cleaning up. It's very portable, I mentioned earlier too. And of course it comes with free world-class support. So anytime there's a problem, you just call the 1-800 number and there's someone active there to assist you and get you going, as well as local support. There's quite a few of us here in Ontario. There's various mounting apparatuses to use. We have a magnetic base, so you have the ability to put it onto an actual fixed, your machine. If it's made out of steel, you can actually magnetize to it, or a magnetic table. You have the vacuum mount for granite tables. It's very useful when you're doing granite table, or when you have a granite table, to be able to just suction right onto that actual table. We have a very sturdy, the rolling stand there you have at the top right. It comes with a standard base plate that you can use just normal clamps, or you can bolt onto the actual product or table that you're working with. We even sell a granite table that has 2 places to fix your arm, as well as the portable tripod that you see here with me today. The Edge, the one benefit to this arm over our other arms is it's got an onboard computer, so you won't be able to see the screen on here from your spots, but on the actual projector you can see. So I've got capabilities to do my measurements. So not only do I not need my laptop to do probing measurements, I can go anywhere and just probe. It's also, I don't even need the power supply because it does have a battery backup. So if I unplug, I'm still running. The arm itself is also capable, the Edge arm is also Bluetooth and wireless capability. So you can communicate without having to plug it in with the actual USB cable. So it's just various screenshots here. So you can do various features. You can do checks. I don't see it on this screen, but there's actual checks to diagnostics to make sure that your mount is level, but also your temperature is okay, and event logs. So if there's been any changes through, say you calibrated yesterday and you want to go back to that calibration, you have the ability to go back to yesterday's calibration, as well as being able to do different measurements between 2 planes. I want to know the length, or 2 points. I can do the measurements there. I can check angles, etc. So in this case, or this example, it's using CAD in the background. So the gray is CAD, and I'm using the probe tip to do measurements. So I was able to measure the circumference, for example, or create a circle around this pin here and get the nominal information from the actual CAD, but compare it to the actual measure and see what the deviation is. And depending on what your tolerance is, the software will calculate whether it's a pass or fail. Brings in all your GD&T information as well into here. If you don't have CAD, you're able to still do your measurements, your circles, your cones, lengths, measurements, etc., from the actual arm itself and create that information. As you can see, it's created cylinders and cones and circles here from the actual probe tip itself measuring. And still gives you a report, obviously not comparing it to a nominal data, but still giving you that information and be able to still do your plane-to-plane comparison, your cylinder information, concentricity, perpendicularity, length, etc. So any questions on the arm itself? We will do a live demonstration after this. The next couple of slides are going to talk specifically about the laser scanning side, which kind of gives me ideas what that's what you're looking for your reverse engineering. But any questions yet just about the arm itself? Go ahead.
Do you have the probes to measure, to do measurements for inaccessible areas? Imagine
We have different tips, yeah. So if it's inaccessible within reason, so we have different lengths, so you can get into deep pockets, for example. You have smaller probes. So I've got a 3mm probe tip on here. It comes with a 3 and a 6 mil, so you can change the size of the probe tips as well to assist. Does that help out? Or?
Yeah, I was thinking of the engine, a combustion engine.
Okay.
There are inaccessible areas where you need to do a 3D analysis to make sure consistency.
Okay, yeah. I mean, there are
of the probe.
excuse me, limitations, but we do have probes that are even hooked or bent, so you can go around corners. It just depends, I guess, how big of an engine and how much room you have to get in. But we do have actual probes that hook in and are on whatever 45 degrees or 90 degrees, and all that is calibrated by you before you do the job, so you can make sure that it's within your specifications. But we do have different probe tips that could hopefully enough to be able to get your measurements for that. Any other questions? Comments? All right, so the FaroScan arm is our next thing. So again, it's removable. You guys saw me take it off. So I can use it with or without. So if I'm doing your engine, I may not have enough room to get the actual scanner in there. I may have just enough room to put the actual probe tip in. So I would take the scan head off. I may need to do a different probe tip, like I mentioned, whether it's extension or a curved one. But now I have the ability to go into much smaller areas. Obviously, this makes it a lot bigger. So this is our 6th generation laser scanner. And when I fire it up, you'll see it's actually a blue laser. So it's using a different wave frequency. Our old ones were red, and they used a different waveform. So I'll just continue unless there's any other questions. But you just shout them out if you do come up with them. So the laser scanner, or the LLP as we call it, laser line probe, is a line probe. So when you see it, there'll be actually a blue line of laser shots coming out of the actual device. And it's collecting that data. The data reflects back into, so the laser would fire out and come back into the camera itself. And that's how we're able to see the part that we're scanning. And it collects that data and converts it to an XYZ location. So that entire line would have, excuse me, thousands of laser shots, and everyone would have an XYZ location. And that is based off of both the distance the laser is firing to the product and back, but then also its reference back to the arm position, so where the arm is in space.
You said it was developed for medical applications.
Originally, yeah.
Originally.
Back in '81, yeah.
Okay. Could it be used for measuring, for instance, bones?
I was actually at the University of Toronto. I was there last week with a company, well, Autodesk or AutoCAD. They have a division that they work with the University of Toronto with doing bones. So obviously they had bones there that we were scanning, and that's what they were using to do some of their research for us. So they were laser scanning the bones. I mean, I can measure obviously with the probe tip, but laser scanning is able to generate, and if they want to 3D print that bone for different applications, they can. Say if they're doing an operation and they want to do
I'm
a
thinking
practice.
of the hip or knee replacement
Mhm.
prior to the
Yeah, I mean, I can't scan through my skin, obviously.
You cannot.
No, it's line of sight, so whatever it hits, so I'll be hitting my skin at that point. But if they had an example, you know, from a cadaver or something, they could use that bone, scan it, and do a practice run. They would be able to do that on, you know, 3D print those out and have an actual, you know, as human as you can get bone to practice on. But yeah, it can't see through anything. It can't penetrate. Unfortunately, it's line of sight, so it reflects off of whatever it hits. It comes back to the device. So some of the characteristics. So it's compact, simple to operate, captures data quickly, and it's highly accurate. So when I say quickly, it's getting every 2 seconds. It's a million shots, pretty much, 500,000 shots a second, and it's able to. Excuse me. We're seeing in this example here. It's a highly reflective. That's the passenger mirror. Now it's not the mirrored side of it, obviously it's the actual painted side, but it's a high gloss. You can actually see the gentleman here scanning. In another image, I actually have him, you know, he's giving the peace symbol, and you can actually make it out quite easily, but highly reflective, but yet we're still able to get a point cloud generated off of that. So reflectivity using the blue laser has been very, very good for the Faro scanner. So we talked about earlier doing leather, and this is scanning leather, again, non-obtrusive, being able to no contact and scan it without putting any pressure on that. Did I hear a question?
Is it able to scan transparent actually?
It can. I mean, I could do this water bottle, but a lot of the light would actually reflect through. There's other ways you could do something that's transparent. You could put, it's called Magnaflux on it. You could spray paint it, a color just to give it something. Like I couldn't do your glasses per se. It may get some returns off of the glass, but a lot of it would actually go through. So you may get a double hit on that.
So somehow first you have to coat the transparent.
Only if it's the transparent, and you'd have to try it. Sometimes it will be fine if you get the right angle. It'll be fine because it's how it reflects off of it. But I mean, I've done tooling balls or like ball bearings, basically highly polished steel, and you're able to get a return off of that. So, but transparent would be one area that would give you a bit of grief, like your glasses or this water bottle. I have done water bottles and it does come out, but again, it's hit or miss whether or not it's actually going to work or not. It depends on your angle of incidence and which way you're hitting that actual plastic sometimes. But yeah, so I mean, I would say black surfaces, shiny surfaces, which is a big challenge because, you know, black really absorbs light, whereas shiny chrome will reflect it, but it's able to get both. It calculates and automatically sets that auto exposure to be able to collect how many, or collect the data based off the exposure of what it's hitting.
So does it do that automatically, or do you have to?
It does do it automatically, and you can also do it manually as well if you're still having difficulties. You have the ability, but this particular scanner is able to do automatically, and it's quite remarkable.
So it calibrates itself if you're scanning a black surface or a shiny surface?
Yeah, it's able to take in the exposure and tell that, hey, no, it's too much, it's being super saturated, or it's not enough, it needs to adjust. It does all that automatically. Like if I scan my hand, for example, I mean, the skin, it's going to absorb a lot of light, but my wedding ring, it's not as shiny as it used to be, but it does reflect a lot more, but I'll get both data from the ring in my hand, for example, like that. And if I scan this part here, you can see it's got the chrome and the black, and I can scan both of those, no problems. I'll get data off of both. So laser itself, like I said earlier, it is a line, so you can see it'll come out, and it reflects back into the actual camera. Reflects back into the camera, so it comes out of the laser, back into the camera, and it does the trigonometry to figure out where it is in space and creates that three-dimensional image. So just, like I said, the automatic scan mode, the question, it is automatic, so it's changing for whether it's a black or a shiny part, it's able to do that automatically. Works with all our edge arms, very compact and ergonomic design. So some of the applications, and so this is referring to, again, just the scanner part being the non-contact inspection. So scanning a part, comparing that to CAD. Scanning a part, comparing it to another part. So part-to-part comparison. If you have a part that you know is perfect, you've measured it, you know it's exactly how you want it. Now you can do the second piece, third piece out of the manufacturing side of things and compare it to one another. First article inspection, making sure that it's, if you need to improve on the part, you're getting the information from that first part, first article done, collected, stored, you have that indefinitely, and have the ability to also compare that to different, whether it's your CAD or your original design. CAD-based inspection, reverse engineering, so you're able to measure directly against CAD. So in this case, you can see how it's color-coded, and maybe red shows too much material, green is perfect, blue is too much material has been removed. Another example up here, you can see where the bend is. Maybe when they did the actual CAD, you're not getting in weld joints or bends per se, so that's why it shows up around the edges here and around the yellow here as well, just because it's the actual, say, weld position. So in regards to how shiny can it be, this is a very shiny metal step here. You can see we were able to scan it. This is a Nikon D2000 camera. You can make up the strap. You can make up the D2000, make up the Nikon here. It's a little fuzzy on my projector. The fingerprint here, for those behind, should be able to see on my laptop. You can actually make up the fingerprint. The Canadian loonie, the trees, the feet, the eye, the feathers, the waves, all the little dots around it. Read dollar on it too. And if you're looking at my screen, you can actually make out the maple leaf on the center here, the circle here as well. So quite highly detailed. Just some more sample data. This is an armrest, I think, from a car. It's hard to see, but there actually are wrinkles right here in the leather, and it actually picked it up in the actual laser data here as well. It's just a 2-inch label from a stapler, I believe. Here's that Nikon camera again. Your data on the left, the actual photograph on the right. It's a 2-inch, or not even, just almost 2-inch little plastic figurine. Your windshield wiper control. Here's that mirror, and here you can see the guy taking the picture and how reflective it is. He's given the peace symbol, and we're still able to collect data off of that. This is a wheel or a shiny rim, and you can see how it not only is it black, it's also got chrome areas, shiny black, and it was able to pick up all the detail and data off of that. And then back to, this is a mold inspection, and again showing too thin material here, perfect being green, and then the red, too much material. So doing inspection based off of a CAD drawing. So that kind of goes through all our presentation on the PowerPoint. Now we'll go to the live demonstration. But do we have any questions specifically? Anything I went through there, or
How good is the cloud data?
in what regards how good, like the accuracy, or so the arm this arm, and there's different sizes as you can see in the brochures. So this arm has a accuracy of 0.029 mil, so just over 1 thou, and then when you add a scanner, the scanner adds about 1 more thou to it. So again, depends on which arm size, but it always adds about 1 extra thou to it. So this arm has setup would be around 2 thou accuracy, plus or minus. When I do a calibration, typically I'm better than that. That's its worst case scenario. It won't pass its calibration if I am higher than what it's actually deemed certified by Faro itself.
It does all the processing on board, so you don't need a computer.
That's a double answer for that one. For doing probing only, so if the laser's not on, I can do everything on the actual arm, on this version of the arm. If I want to laser scan all that, it has to be into a computer of some sort.
And then transfer it.
So if I'm not connected to a laptop and I'm just probing, there's a SD card and a USB card here that I can plug in. And then if I'm going to do the scanning, I'll plug in a USB cable right into my laptop, and it'll scan and convert all the data and process it and store it all on my actual laptop. So when I do that in a few minutes, you'll see it. It'll just be saving to my hard drive, not to the arm. There's just too many points. Every couple minutes, a couple seconds, a million shots is quite a lot of data.
I'm seeing 280 frames.
Yeah, exactly. Yeah. So it's unfortunately, yeah, that part.
It is a
can't be
USB connection, not a Ethernet.
There's Ethernet, USB, and Bluetooth and wireless. For the scanning, I always go USB because wireless can do it, but it's not quite as quick as I'd like.
So why do we have a Ethernet? Why not just?
Well, you got to remember this is also designed just for probing. So if I want to do just probing, I can do that over the wireless. I can do that in Bluetooth, no problem. But when I'm doing the laser scanning, I really need to be connected through the USB cable.
And do you need like a big machine?
For processing laser data, you really do need, a high-end computer. For probing, you can use a basic computer, but for the laser scanning, millions and millions. I mean, if I scan, I might have 20 million points, and that's a lot for any computer to process. So it's very RAM dependent. Very good video card is important. You want to make sure you have a good video card in there to be able to visualize the actual point cloud and move it around. So those things are definitely things you want to keep in mind or consider when you're doing purchase.
But I hope if I have a slow machine, then all it will do is just slow down the process and not do overflow.
It should, yeah. I mean, when I do a scan, you'll see. I mean, it'll take my computer. This isn't my actual computer. I had to order a new one last week. It died. This is my training computer, but it's not. It doesn't have solid state drives on this one. But if you have a computer with solid state drives, it's really quick. Versus this one that you'll see a lag or hesitation as it's processing all those points. And if you have a slower computer that doesn't have as much RAM or is an older computer or the video card, yeah, it just adds more time to your actual process.
In the end, you're not losing anything.
No. And I also have the ability to display, say, one of every 32 points or a quarter of the points, but all the points are still saved on the hard drive. I'm just displaying it differently. I'm only displaying a fraction of it. So I have the ability to do that too. Any other questions? We get into the live demo.
Okay, do you want to get those 3D printed products?
So the scanning on those.
Sure.
Okay.
We'll just
We
grab
can
one.
find out whether they were 3D printed properly.
Like I said, I'm going to actually plug in directly just the laser scanning side of things.
You need to do the same. You just answer it right. It's later than normal. Do you think there's
So threading is going to be tough to get, or we can try, but threading is tricky.
depende of which category?
So I'll just, before we scan your multiple parts there, I'll just do a quick one and show you how it works if you do have the CAD. So this is the CAD for the piece that I brought in with me. So what I'll do is I'll align it first off so that it's in the same, it's in CAD coordinates rather than ARM coordinates, which it would be right now. And then I'll do some scanning, we'll do some probing just so you can see the two working hand in hand. And then we'll do some of your parts thereafter. So what I'll do is on the actual CAD itself, I'll just pick 3 planes. Just gonna pick we'll just say top, side, side, and then I'm just going to align those there. I picked them on the CAD. I'm going to do the same thing, but actually probe them. So probe those. So one thing, I just got this. So right now I'm just going to probe. So I do have the 3mm probe on here. We can go up to a size of like an inch, as big as you really want. But with the 3mm probe, I'm able to get into tighter coordinates. So if I want to get into these smaller little pins, for example. But for probing, I'm just going to I press the, you can kind of hear the noise. I don't know if the volume will go away. So I'm just touching. And then I'm going to pull up. The reason I'm pulling up when I tell it to stop, and you hear that little bing, that means I got it and created my plane. It's actually offsetting it by 1.5 millimeters to get the center of this probe tip. And then the last one was in this corner here. So I got all of them. And now it's just as simple as coming over to the computer and doing a quick alignment.
When you move the arm, it automatically rotate the caliper.
Hey, once I'm aligned, yeah, once I do this, you'll see. So we're going to say plane 1, 2, 3. So now when I move my arm on top of the actual part, it should I got it. Oh, I'm going to measure something, sorry. So I'll grab the circles, for example. And I'm going to actually probe these. Yeah, you can see as I move it around, and if I sit it in one of these holes, it's very faint, but you see the little red as I move it around?
Yeah.
So if I come here, I'm circling here, you can see how it's circling on the screen. So now it's a line that's in CAD coordinates. So I'll just do some quick measurements. So just do this circle. And I slipped off and it knew that, so it catches you. Say remeasure. And do the big one. I can do even some small ones. Now we see the measurements. So we measured so this circle here has 100, I'm in millimeter or metric, so 100 millimeters. And what I'll do is I'll just grab so that's 100. So you can see it shows the deviation between the two. Down here, these circles I measured, so this one's 19.84, 19.75. This little guy, 5 mil, is 5.159. So it's quickly measuring just using the probe tips, and I'm aligned to the actual CAD itself. So anything I measure, whether it's the slot, this rectangle here, this angle here, this cone here, let's do the cone. I'll get the information and the angle that it's actually in. A bit tricky because I'm on a table that moves, not a granite table. We'll try to push a little lighter. There we go, our cone. So you should see it just created a purple cone there and with the information. If I go to that cone, yeah, and I've got multiple things I can add into it. But for example, it's showing the angle is 30 degrees. And I can, whether it's taper angle 1 or taper angle 2, so 15 degrees or 45 or 75 degrees. All that information I can display. I can also have it do different GD&T information requests as needed. I can also construct, so if I had, I'm trying to remember, so I did circle 1 to circle 3, if I just want to know the distance between those two, and the distance 129.360 millimeters. If I can make that any less fuzzy, but no. You may have to look on my screen for the actual numbers. But the probing also, I was doing it single shot. I can also continue, so I can drag the scanner on top. So if I wanted to do, say, the profile on the outside, just show you. And whether it's by distance, and I can set the distance whatever I want, or by time interval. But when I drag it, so you can see how I trace that outside. I mean, if I had my hand here, fingers. So capabilities there as well. But for the scanning, any questions on probing?
Does it matter if the probing tip is at an angle? Doesn't matter, right?
No, because you calibrate it, it's always finding the center of it. So when I do that circle, for example, it doesn't matter which side I hit of it, it's always going to force the actual measurement to the center of that point tip, because I've told it that it's a 3 millimeter probe, so it offsets by 1.5 millimeter.
What is the accuracy of the measurements? The accuracy.
Oh, okay. So this particular unit for probing would be about 1,000.
1,000.
Yeah, plus or minus 1,000. So we're going to use the same part, and it's been aligned. I've got some measurements, but now for the actual scanning. I have the ability. I'm going to do it as a point cloud, but I can also in this software go right into it as a polygonal mesh. So you can see one of the things I'll point out is on the roof, the blue is the actual laser line, and the red is literally for targeting. So I want to get those to intersect as much as possible. Right now on here, I'm showing red, or if you look over here, that's the range. The green, it's past its range. So red, I won't actually collect data if I press the button. I want to be keeping it on top of each other as best I can, intersecting. And you can see how once I do that, it goes green, the arm itself. So I've got visual on the computer to say I'm within range. I got the visual on here, and also the sound. So if I'm here, it won't collect, whereas when I'm here, you'll hear it actually collecting the data set. So I'll just do a pass over this part here. I just press the green button to start. And then, come on this side to get some of the edges that I'll have missed. So I'm just filling it in. Again, it's line of sight. So in order to get to this angle, I have to be able to see it. I can't do it from above. Spill my coffee. That's the clamp hitting there. So it gives me a visual representation of what I'm scanning. So if I need to go back, it looks like I've got everything. Maybe just back here, I can get a bit more data. Actually, a lot more data back there. And as I was saying, it should be getting, yeah, you can see how it's getting this chrome. Which will be interesting because it may actually be sitting on the actual CAD. I've got a few different plates, and I know one of them is off. I don't know if it was intentional when they manufactured it. But I've got the data, and then what I can do is I can clean up all the data and get rid of everything that's not part of the CAD. I'm just going to finish that. So that was pretty quick, but that's where you see the difference between a slower computer and a faster computer. Actually, my alignment looks like it's slightly off, so I can realign that too.
Can you rotate the specimen and do the scan on the other side and then combine?
Yes, you can, yeah. I just touched up the alignment there because I wasn't too happy with it. And that's highly possibility that it was just the table shaking. Okay. So now I can do a, oh, sorry, I was going to do, so select. Elements based off of. What it's done is collected everything that's within 2 millimeters of the actual CAD. I'm going to invert that. So now it's everything that's not close to the CAD, including, you can see how I've got the clamp. And I'm going to actually leave this one in just because, yeah, this one's off. I know that. And then I'm just going to delete everything else. So first off, I'm deleting it because it could be 2 million, 3 million points of just a tabletop that I don't care about. So get rid of it, but it also makes it look a bit cleaner. So now I've got just, I've got the demo CAD, I've got the scan data I just did, and then I got both of them together. Excuse me. I'll just do a quick comparison. Same one. So quick comparison showing, so anything, it's hard to read on the projector, but in the green and the blue is between, so 0 to minus 0.2 to plus 0.2. Anything in the red would be a millimeter away, or in the purple negative would be, in the purple would be also a millimeter away. So you can see this actual bar itself is off, and for whatever reason, that's just how they build it. Maybe it's a test for us. I'll tighten this up too, just to see. So again, yeah, so anything in the yellow and red starts to be more than 0.2 millimeters.
So this is still the point cloud data, right?
This is the point cloud data compared to the actual CAD.
So you have to do so before you get the CAD file, so you can do the reconstruction, the surface, within this software?
No, this was just to show you how to do it with CAD. I'll do your parts now, which I don't have the CAD for, and we'll still be able to scan it. I just won't be able to compare it to anything because I have nothing to compare it to.
For example, say I scan the part and then I need a CAD file. So this right now is not a CAD file.
No, okay, I got you, yeah. So I can export this, as a polygonal model. So right now it's saying IGIS, SQL, state, all the different, POL, Autodesk, DXF, all the different versions of solid models I can export to. I will put a disclaimer in there, though. It's not a true STL that you'd be used to getting out of your SolidWorks you said you used, right? It'll be 80 megs versus 1 meg. What it's doing, it's taking every single one of these laser point dots and just making a triangle out of it, connecting the dots. So in order to get it to that next step, there's a software called, with this program, you'd use IM-Edit, or IM-Model, and it models that, puts a skin over it and creates a true STL. There's another program, Geomagic, DesignX, I should say, DesignX, that does the true shapefile. And if you're using DesignX, it'll actually export it and rebuild it within your SolidWorks as if you designed it in SolidWorks. It actually rebuilds it in SolidWorks, which is nice. But yeah, right now it's just a point, and I can export it as a solid model per se, but it's not what you'd be used to. It's not a true SolidWorks kind of solid model.
You can still export it as a point cloud file, right?
Yeah, I can export as a point cloud or a polygonal model. Yeah. And if you have software that can convert it, then you can also do it that way as well. Yeah. So any questions, or do you want to see me scan your parts now? So I'll go to, I guess the cylinder one. So I'll just turn on the laser scanner again. Now, threads on screws or bolts, which is exactly what you brought me. Typically, it's a standard thread, and you would just do that yourself, put the thread in yourself. But I will scan it. I'm going to set it to fine. Again, the table could move, but hopefully it'll be steady enough. Okay, we're going to fit in the hole. And you said this was 3D printed by one of your machines? Do you have 3D printers here then, or?
We have one 3D printer with this piece was 3D printed in Niagara Falls.
Oh, okay. So for that, okay, so almost 1 million shots. I did get the thread. It is missing a bit. You can see blue here. That's the back side of this side. So I could go over it a bit more, but it actually I could calculate the thread from here. And you can also see I came from this angle. I really need to get underneath to get the bottom, so you would have to put in a different apparatus to be able to scan the bottom to get underneath. But from the line of sight and the angle I came, it turned out really well. I'm actually quite happy with that. So some things.
There's also a fine detail inside this one. Can it catch the
Like at the very bottom, probably not. I'll now that I've moved it, I'll rescan it afterwards to the center to show you how far down I can go, but I won't be able to get too far. So I'm just gonna turn that on. Gonna get rid of all that extra data. So some of the things, instead of probing to get measurements, I can now, if I wanted to know the diameter of this, I'm gonna do it to fit. And there are different options. I'm gonna do best fit, but I can do min max. That's gonna fit a cylinder to there. And it's saying it's 19.769 mil. I don't know what I printed it at, but that's what I'm measuring it at from the data. I can also, if I wanted to cap it, I can check how big it is. So if I put a plane on here, I'll just do a basic one. On the bottom. Doesn't really matter, I'll use the table because it will be just as flat. And then if I do a comparison or measurement between those two, 53.626 mil. I'm told is exactly the right measurement. Not a lot more I can do with this shape, but so I'll scan it again, just concentrating on the center. I'll do this, so that's scan 1. I'll do this as scan 2. I'll do this one as a polygonal model just so you can see how it'll polygonize it. And so what it's doing is taking the point cloud, but then automatically connecting the dots. So this is where it's going to be tricky just because it's such a narrow tube. I probably will have some difficulty getting the laser all the way down, but let's try it. And I actually put it almost in the exact same spot as before. But it's still processing. It'll take a second, and then once it's done, this is where a faster computer, you asked up there, faster computer would help, or a solid state drive. Okay, so I'm happy and finalize. Okay, so I'm going to hide the first one. Yeah, so you can see I didn't get much data down below, if any. I did get a bit of the sidewall here, but that, one of its limitations is the convergence of the camera and the laser is so far apart that it can only get so deep into things. So I could probably get a bit more up here if I came from a different angle, but what I was aiming for was the bottom, and it did give me something down there, but not really usable data. You can see the stamping on the tool that's underneath it. Quite easily make out that's a 020, but
I guess the reflection is not going back to the camera.
yeah, and I mean, I don't know if it's if these were closer together. I mean, it's literally it's wider than that, so I'm trying to get it to converge. I have to pull it up from that part, but then I get too far away from it due to the range. So there are that limitation would be that's where I would go with the probing kit now and go in and have an extension probe and probe down there if I needed the measurements down below. So I have the ability to use it now and do the probing at the same time. Was the screen, was this just part of it, or you want me to scan that? Is that a 3D printer too? Yeah. It looks like it. What I'll do. And was it the circuit board or the lens you wanted? The circuit board, I guess? Or
Yeah.
Scan this side?
Or the transfer of the transfer.
All right. Let's see. So I hide these.
They're a pain, huh?
They're really a pain. I gotta demo tomorrow, guys. Like, I got a really, really intricate hard part frame.
Start with them with it, you know. Really different part with the threads, you know, and then maybe like
I got it. I'll just do it as a standard. But scan.
it's easier to scan an engine blade for a turbine. You know?
It is.
I mean, it's just you know. It's
Sorry for blocking that. Okay, so this part will do first. So it does warn you that it says misalignment. That's again, if I'm on a granite table, not a problem. Zoom. Yeah, did I get it?
I guess you can put the mouse here.
Yeah, that would actually make more sense. Now do your circuit board. So I am getting return, so that's actually better than that. I'm just gonna accept that. Keep. So little button part there. You can see a little knob on that. I'm not sure what that's for, but the knob even came out pretty nicely. And, sorry? So here, it came out pretty good. There is, I do see a little bit of, that's probably the angled insert, high reflectivity, so a bit of noise here, but I was able to get most of it. Yeah, right in the center for some reason. So that's probably just the being highly reflective and coming back into it, or it's actually going right through and hitting the back part of the transparency glass. Yeah, I'll show you.
Sean, do you want to share?
No, I'm fine. Thanks. So, showing here, you can see my actual. All right, I'll take it. Thanks. You can see the material in the shirt came out. It's easy to see on my screen because it was behind, but you can see I got the actual lines of the cotton and the stitching here came out really nicely. All my lovely wrinkles in my hands.
Some moisturizer.
I do. No kidding aside, I've been every night. Like, I don't know what's wrong with it. My nose is too dry. My wedding band and my nails even came up pretty good on this one. But I do need moisturizer. Not so much. You can even see my arteries and veins. So. The outside, the skin covering the arteries and the veins, not the actual arteries themselves. So, yeah, is there anything else you guys wanted to see? I can export as an IGES, and I'm more than happy to export them as an IGES for you, get a memory stick or whatever. But it could kill your CAD. Like literally, it's going to be a ginormous file. Lastly, I don't know if I can, because it's on my computer. Let's see if I have it. No, I don't. I'll have to send you a link, but for the reverse engineering side of things, I've got some examples. I just don't have all the software on here to show it, but there's different ways. I can either, back in this software, create cross sections and create reverse engineer parts based off the cross section of your X, your Y, and the Z. That's a quick and dirty way to do it, but also the capability of actually taking this file, polygonizing it, and taking it into either IMmerge, IMedit in PolyWorks World, or into DesignX software to do a proper full reverse engineer application on it. I do have examples I just can't show you because I don't have that software on here, but it's quite remarkable how detailed, and it's nice because you can actually compare to, say if I was to scan my phone, and I'm in the software, I'm going back to the point cloud and being able to show any deviations from the new CAD file I've created. I can show where I'm off, how close I am, just like I did the colorized map showing the inconsistencies to CAD. I'm now showing that to the CAD I'm creating as well. So you have the ability to work that way as well, which is quite nice.
So to create a CAD file, this application is not part of this, right? It's a separate file that where you have to import the cloud of points.
Yeah, and there's different ways. So some software will allow me to import a point cloud. Some software you need to polygonize it, so I could export this as a polygonal file and take it to the next. So if I go to this main window here, not that one. So you can see this is IMspec, that's where I was. This next one is called IMEdit, and that allows me to edit that model and create your reverse engineered part in this program. That's up here now. So it allows me to do different things, but there's also, I can take a point cloud into DesignX or GeoMagic is the same.
So are you offering this software too? Or?
I can. I mean, the sky's the limit.
Related.
Yeah, so Faro makes the equipment, and then we also are resellers for all the software. It just really depends what the college is looking to get in the end. And you know, if you already have some software in-house, you may not need it, or we can direct you in the right place at that point. But yeah, we sell not only the hardware, we also sell the software.
For maintenance, what would be the
Also depends if you're buying an arm and scanner and software, there's different
Assume
packages.
this machine,
Well, the arm
scanner and the
be about 5,000-6,000 a year, depending on the size of the arm, things like that.
Do you have different versions of the scanner or?
So we technically, yes, we have the older version, the V5. We still have those around. The difference being is this is 4 times faster and has the blue light, so it's better on the bright shiny things versus the predecessor, the V5. Doesn't quite have the capability to adjust it that fast. It's a bit more manual, and like I said, it's 4 times slower, 3.4 times slower. It's still an amazing scanner. It's just not as quick as this one.
But the same principle.
Identical, yeah. Anytime we're getting the accuracies we're getting is due to the arm, you have to have it attached to the arm. We do have the one, I think you missed the beginning, but we do have a different, I'll show you it. So this is our freestyle. This, I can scan this room, I can scan this table, I can scan this computer, but I'm not getting the accuracy. I'm at 1 millimeter accuracy, which is still pretty tight, but for machining purposes and metrology side of things, it's not tight enough. And then I'll just show you, since I've got this now. Our newest one that we just came out with, this is our Cobalt. Literally, I think it was 2 weeks ago. I just got trained on it yesterday, and my first demo was tomorrow. But it's you don't have a projector here, but it's a lot bigger than my projector. It's so 12 inches by 10 inches, and it's structured light, so it's projecting out an image, line pattern, and taking that information in with 2 cameras. So it's got the 2 cameras, multi-array, and is able to then calculate your point cloud based off of that. So we also have structured light, or a lot of people still call it white light. This one actually is blue light because it's a blue LED light bulb in it. But it allows you to do there's your pattern. So it creates the pattern on the part, and from that, I don't have an example, but it creates the same point cloud that you would have seen from the scanner. Pros and cons. I mean, it's more automated. You can put it on a robotic head. You can put on a rotary table, put your part on it, and have it rotate. Whereas with the arm, I'm moving my hand around the part to get it. But I have the ability now to get into deep crevices and corners that you may not see from just one particular angle with the structural light sensor. Other questions? Comments? Yeah.
We can suggest a solution if you are planning to improve the hardware.
Gladly.
I'm noticing that you're using USB interface.
Mhm.
Maybe we can think about migrating this to include a wireless connection.
It does have it actually. So
you have it?
yeah, it has Wi-Fi, Bluetooth, internet cable as well. But for scanning, I find for me,
Slow?
it's a bit too slow, so you have to hesitate a bit more. So for the speed, and if you have a way to speed it up, I'd be glad to hear that. But for the speed, I typically do the USB for scanning. For probing, it's fast enough over Wi-Fi because it's just a few points. But when you're sending, every couple seconds, a million points, it really bogs it down quite a lot. But we do have, yes, yeah.
Beautiful.
It does help. Thanks.
Have for probing, you have 1 power source inside.
For this one, we have smaller arms that are tighter, and then 12-foot arm that's about 2
And
hours.
what about the point cloud? What is
So the laser itself is 1 thou, but on top of whatever arm it's on. So if it's on the 12-foot, it'd be 3 thou. On this arm, it's 2 thou. 1 plus 1, 2. Does anybody want to try it?
What about the other scanner? The new one?
The Cobalt, yeah.
What's the actual?
So it depends. There's 2 lenses right now currently for it. There's a 250, so you got a focal view of say 10 inches, and then the 500, so about 1.5 feet. The 250 is 1 thou. The 500 is 2 thou. So it just depends which lens.
Comparable.
Yeah, well, the 250 it's tighter, but you're getting a much smaller surface area, right? So it's comparable is probably the best way to say it, yeah. And the nice thing is with the arm, you do have the ability to still probe if you need a specific circle or a cone or a cylinder with tight accuracy. I'm still going to get the 1 thou from the probing because you're always going to have the tightest tolerance from that. And then I still have the ability to laser scan on top of that. I don't know if I have any-
Your database, do you have the chat file of medical devices that you said originally the company was?
It's all industrial now, so they didn't consume a lot of medical. So I mean, you can still use it for medical purposes, but it's not designed for that.
So does Faro also have a SDK if somebody wants to use a scanner for custom application?
Yeah, you still need an ARM, but we do have SDK capabilities, like so you can run it in your own programs. No, I thought I had. I don't think I saved them. Yeah, so this was just from the structural light scanner. It was just a toy little tank that I scanned yesterday. You can see the turret and everything. So that was four scans from 4 different angles on a rotary base that did that.
Like a Sherman D4.
It claimed it was Wolverine's tank from the Avengers. Wolverine from the X-Men. I don't know why you'd have a tank, but anyways. It was a kid's toy that we were scanning. And, any other questions regarding the ARM, the Cobalt, Faro in general, other software hardware we have? Does that
Nice.
kind of answer all your questions, hopefully, or?
Nice.
Sorry?
What's the price?
Oh, price. I don't need to worry about such things.
Now the manager's questions.
So if you buy an ARM, this ARM, this is the 9-foot with the actual scan head. They're so the ARM, yeah, so it'd be about 75,000 list price. And then there's different software packages, so it really depends on what software you go to and how far you take that software that it adds up more and more.
75,000 Canadian.
Oh, you wish.